My research aims to study the behavior of piping equipment systems in nuclear power plants using advanced simulation techniques, and also to predict any potential degraded locations in real time. To avoid nuclear power plant accidents, such as the Fukushima Daiichi nuclear disaster, understanding the behavior of such piping equipment systems and maintaining their integrity is extremely important. Over the course of time, degradation in the piping equipment systems can occur due to erosion and corrosion of the system. This degradation often leads to a reduction in the modulus of elasticity and the cross-sectional area of the piping system. Therefore, it causes a reduction in the stiffness of the system. Previous studies have shown that degradation in such piping systems usually occurs at the nozzles, elbows, and T-joints. For this study, a nuclear power plant piping equipment system is selected from the U.S. Nuclear Regulatory Commission piping benchmark problems, and the degradation is assumed to take place at either the hot leg nozzles or the cold leg nozzles of the reactor pressure vessel. We use ANSYS software to simulate a degraded as well as non-degraded piping equipment system using 3D finite element modeling. A minor degradation at the nozzles is represented by a 25% stiffness reduction at these nozzles. Uncertainty is also incorporated by introducing 20%, 25%, and 30% stiffness reduction. The piping equipment system is subjected to various seismic loads from 56 earthquakes, and Python codes are used to carry out these simulations. The response of the system is captured as the acceleration time series response at predetermined sensor locations. This sensor response data is then converted from a response in the time domain to a response in the frequency domain, called the power spectrum density. Changes in the power spectrum density peaks and corresponding frequencies are extracted from the sensor data. This data is then used to build a training database for an artificial neural network. It is observed that the artificial neural network can predict the degraded locations with 92% accuracy, which is within the acceptable levels of confidence. For the next steps in the study, we will introduce degradation at other elbow and nozzle locations in the system. We will also try to predict the degraded locations as well as the severity of degradation.